Right, it is my very great privilege and honour to introduce an old chum of mine, James Davies, who has more titles than I have. He's a fellow, he's a VP, and he's general manager of the machine learning group in ARM. So, Jem's going to come and talk to us about, well, guess what? Stuff, yes. Do come over here, old chap. I think this is still the same one. Is this the button we need? Yeah, that works, right.
Technology?
Right.
Good man. Nursey will be along later to help you out. So good morning, everybody. My name's Jem Davies, as Dave Rustling says. A long time ago in a galaxy far, far away, he persuaded me to join a company called ARM, where I was a Linux kernel hacker. And the stories that are told of those times, tragically, are mostly true. More years have passed now than either of us cares to admit, and now I'm an ARM fellow, and recently I took over as general manager of the ARM's machine learning group. What am I doing here today apart from reminiscing with an old buddy and drinking too much in the bar? I'm here to talk to you about steps we're taking to enable developers to use machine learning across the widest variety of ARM-based platforms to enable us to take advantage of this great technology that Chris was talking about. It all went past so quickly, I think I agreed with several of the things he said, but I'll have to think about it later to see. I think he set me up rather nicely for this talk. How will we do this? Well, we're going to do this by driving the definitions of open standards in this area and collaborating with you, the best in the industry in open source. Damn, it works. What's happening? Machine learning changing incredibly fast, as Chris was talking about. It's a field of really, many moving parts. But we believe the time is right when key areas and applications and use cases are starting to stabilize, and the time is now right for collaboration. I want to thank George for his keynote on Monday, and in that you'll have seen that Linaro announced a new machine learning intelligence initiative that ARM is going to be part of, and I'll talk a bit about what part of means. This initiative, Google announced their endorsement of this with a statement, and I quote, "The TensorFlow team is excited to expand support for edge devices, and we're looking forward to integrating with the ARM-NN library." Right, well, there's a clue. What are we doing? We're getting involved. We're collaborating with all of the companies to define these open standards to support this machine learning to be rolled out across a wide variety of platforms. In addition, we're donating a huge body of code to bootstrap this initiative, and I'm going to talk about that body of code in this talk. Although we were already open source under an MIT license, we're donating ARM-NN to the Linaro Machine Learning Initiative. ARM-NN is an inference engine designed for efficient inference running at the edge on the sort of devices we all work on. And following really quite significant pull from a number of companies working in this space and developers who wanted to get involved and contribute to this project, we decided that Linaro is the best place for that collaboration to happen. So we're donating it to the initiative, remains under an MIT license, very permissive license, and we encourage contributions from everybody. The governance will be organized by Linaro. We think this is the right thing to do. We will continue to work on it. There will be massive contributions from us continuing. We are moving all of our development into the open. So if you don't want to see how sausages get made, I suggest you stay well away. So I think by now, particularly after the previous presentation, nobody would doubt the effect that ML is having and will continue to have on all of the things we're working on. Notwithstanding the absolute massive hype, and Chris, you may have noticed that Gartner put machine learning at the absolute peak of inflated expectations. I paid good money for Gartner to come in and present the Gartner hype cycle to us, and then they put machine learning at the peak of inflated expectations. So imagine my disappointment. But actually, if you're right, ignore all the hype. If you get through it, we will see that ML is enabling key new use cases and also massively improving existing ones. And in something that is perhaps surprising to some of us, if not all. We're seeing this actually across the full spectrum of devices, right from very basic Cortex-M microcontrollers through Cortex-A, through GPUs, and also dedicated neural network processors. It's probably easier to try to list the segments that aren't using machine learning. An experiment that I was recommended, and I recommend it to you, is think of any classical method of processing algorithms, whatever, and just type that in and add machine learning, and then put that into Google. And you'll find a whole range of research papers coming out where people have tried the most bizarre topics and replaced them with a machine learning implementation. My personal favorite is intercontinental ballistic missiles. It's actually a very difficult control plane problem, and very few countries have actually ever got it right. Controlling rockets by lighting a very, very big fire at one end and then moving the other end a bit, it turns out to be remarkably hard to do. All you need to do is write a model of that system, crash about 4 trillion rockets, and then you can have a machine learning process run that for you. It's just extraordinary the things you can apply this to quite successfully and get better results for many values of the word better. Cheaper, faster, more optimized, you name it, you get it. I've listed a few on this slide. I don't think really I need to go through them. I think you all know them. Autonomous driving is only ever really going to take off successfully once, in technological terms, there are many litigation and liability issues to sort, but in technological terms, once the ML advances become mainstream, both in classical sort of object detection and segmentation, but also the cognition that goes into it. Face identification really only got critically reliable once we applied ML techniques. Speech recognition's gone from isolated keyword recognition through to being able to analyze continuous streams of speech using a very small percentage of the CPU budget on sort of mobile devices. Huge improvements in existing capabilities. And image processing, I think, is going to be a huge thing in the consumer field. It's actually, if you think about it, it's an ideal target. Because what do we want? We want things to look good. Can we actually define good in algorithms that say, oh, take this pixel, sharpen that, bring down the gamma, do this, do that? No, we can't. Actually, it's completely heuristic method. So it's ideal for putting vast quantities of images up, getting people to vote on whether they like them or not, and having those images processed in a way that makes us feel, oh, that's nice. Oh, I'll buy that one, not that one. A neat side effect is something that I was working on before in the image processing field, which is actually different groups of people have different ideas about what good looks like. There's a body of work being done to look at genetic disposition towards perceiving color and image in different ways, for example. This just falls out. You just go, I'll have that version, please. I could go on. We could be here all week with me talking about applications that are possibly slightly less exciting, like logistics and distribution and things like this. But one thing I bring out from all of these things is that all of these are decisions where the data is available at the edge. If training is a problem which is solved where you have large quantities of example data, high quality annotated data, then inference is something that you want to do near the test data. And generally speaking, that is at the edge on battery-powered devices, which, curiously enough, is something we care about a lot. Technology. So if we look at machine learning and look at the challenges associated with it, and Chris talked about some of this in his talk, we have problems in different domains. Okay, that's slightly scary. Please don't do that again. You could be an ML domain expert, a data scientist or somebody working in ML frameworks, a researcher. You could be a problem domain expert. You could be a doctor, a logistics planner. You could be a computational linguist. Or you could be a platform expert. And at the moment, you've got the situation where some sort of domain experts are providing their knowledge and expertise to the ML researchers and to allow some experts to interpret the data. But this sort of knowledge and expertise transfer between these different domains is not working well, and it is holding us back. Linaro is obviously the meeting ground for the third pillar, the third domain expertise, which are the platform experts. We are the ones who need to get our heads round Chris's final problem, which is enabling ML across the wide variety of ARM-based platforms. And obviously ARM is committed to working on this part of the problem, and in fact have been working on it for the last few years. Most of the use cases I talked about there, and I think, yeah, that is actually legible, they run on CPUs and GPUs today. But we're going to need to transition some of those to working on other types of processors and accelerators. And those accelerators are not going to be a one-size-fits-all problem. We're going to need different accelerators to solve different computational problems in different markets. So naturally, you know, as a software engineer, or at least was once a software engineer, you know, I reach into my toolkit of things to deal with this, and I come up with a software abstraction. We've got lots of machine learning being run on ARM platforms today. We've got lots of new use cases coming along. We've got some people running perfectly happily on CPUs and GPUs today. We've got some people who are never going to need a neural network accelerator, and we've got some people that do. And we know that we can't rely on the cloud in this situation because it's inappropriate for a bunch of reasons I'll talk about next. But you're going to want to run more efficiently on future devices. You're going to want to run workloads between different parts of the device. You're going to want to run workloads between different devices, and we need to move workloads between the different accelerators. There's a whole heap of choice here that non-experts in this field are currently failing with. We need to make that easy for them if we are to get the benefit of bringing ML techniques to the sort of devices that we build. And standard software inference engines is going to be part of that problem. I talked about running software at the edge and why I thought the cloud wasn't the right answer for everything. It's instructive perhaps to look at a little bit of history here. Most of the ML research has been done by people who had a hyperscale data center out the back. So the obvious tool to use to solve their ML problems was the hyperscale data center. But actually, there are very solid reasons why that isn't going to work for all examples. Clearly going to work for some, it's clearly working for some today. But in the future, there are three primary reasons why there are pressures to move that to processing at the edge. Laws of physics, laws of economics, actually the bits of economics I believe in, and the laws of the land in several jurisdictions. So if we look at the laws of physics, first of all, bandwidth, there is not enough bandwidth in the world. We're talking about upwards of billions, possibly a trillion. My new boss, Massa, who runs SoftBank, talks meaningfully about 1 trillion connected IoT devices. I can't count that far, but it's going to be a big number. Many of them are going to have high-resolution video cameras attached to them. Connecting 500 billion devices and sending a continuous video stream up to a data center in Seattle, having it processed there or in some data center of your choice, submerged under the sea off Iceland, whatever, and then send it all back again. It's just not going to work. The internet will break. There is not that much bandwidth in the world. Power. Increasingly, of course, as we get into modern devices, it's more power expensive to transmit the data than it is to compute it locally. And that's before we start looking at the power consumption of these huge data centers. You know, the power problem, for us, you know, we have some power problems we understand about batteries and things like that. They have similar power problems. Believe it or not, it's actually almost impossible to get more than 10 kilowatts into a rack full of computers and then take the 10 kilowatts of heat out. It's almost impossible to get more than a megawatt into a shipping container and get it out again. You know, they have serious power problems. And then, of course, you have to buy that much power. Stop me later and I'll tell you about the bloke who wanted to run the Human Genome Project and got told to build a power station. So, yeah, the power is significant. Latency, we're accustomed to talking about latency as a user experience problem. You know, we all hate it when the thing doesn't seem to respond to us. You've watched me struggling here. But actually, latency gets to a point where it's rather more than simply tedious. You can imagine a car doing visual recognition of things in front of it, the speed with which it recognizes a speed sign or a stop sign or a child walking out in front of it. is actually singularly important to the process involved. And you just imagine what that says when you go, ooh, sorry, I need to retransmit that. The 3G signal's a bit weak. Yes, 4G makes that better. Yes, 5G makes that better. But it's never going to make this problem go away. There are certain classes of computation we're simply going to have to do locally at the edge. Moving on to cost then. I can do no better than quote Google, who said, if everybody in the world uses Android voice assistant for 3 minutes every day, we will have to double the number of servers we own. So this is not we're not finessing a bill of materials cost here. These are simply eye-watering sums of money that we cannot ignore. It's cheaper to provide a certain number of compute cycles in a small battery-powered device than it is to provide those compute cycles in a 5 nines reliability data center. It just is. And we can also get into questions about who pays that cost, but that's a sort of an interesting aside. Reliability, well, I talked about the interruption to your mobile internet service. There are certain things that just simply have to work. We have to guarantee their performance, we have to guarantee their reliability, their latency, and so the only way to do that in some cases is to take ownership of that problem ourselves. I'm not having a go at the cloud. The cloud is brilliant, but we need to be thinking about using appropriate tools in appropriate places. And then finally, the law of the land, having been through the laws of economics, let's go back to the law of the land. Security and privacy are, of course, concepts that are becoming incredibly important to us. And as we get into the Internet of Connected Devices, then there are significant concerns expressed in that place. We're connecting very personal data. If you think about the phone in your pocket, its accelerometers can already work out with about 90% accuracy what gender you are. It certainly knows when you're sitting down, when you're walking about. It can easily work out when you're asleep. It knows where you are. It knows whether you're in your house, somebody else's house, somebody's house you shouldn't be in. You know, I could go on. There's very personal data here. We are going to want to protect this carefully, and part of the story of protecting that data carefully is not sending it to other people unless you absolutely have to. So I think I've set out, you know, pretty clearly why I think there are fundamental principles. This isn't just me saying this is a good idea. This is observing there are fundamental things, laws of nature out there that are going to push as much as possible of this processing to the edge. And what is that processing? Well, at ARM, we see machine learning as simply, and yes, I deliberately put sneer quotes around that, simply a software problem. ML is for us just a compute workload. It's, of course, an increasingly common workload, and it's a slightly different type of compute workload to some we've seen before, and that has effects on our processor design. But at a high level, we just need this workload run as efficiently as possible, as optimized as much as possible across the widest variety of our platforms. The guy at the top of this stack doesn't care what's in the hardware underneath this. He just wants it to run reliably, easily, and for him not to have to spend all night getting it to work. He likes to go home on time. That was a non-gender specific use of the word he, obviously. So we need a software platform that will support this. And we need to plug into the existing ML frameworks that are already out there. We've been working on parts of this solution for some years now, and last year we announced Project Trillium. We don't have all the parts. We don't intend to have all of the parts. We intend to take the best of the parts from other people and build this, this platform together. But by now, we've got the best part of 100 engineers working on the frameworks that are set out in this rather beautiful architecture diagram. We have our inference engine, ARM-NN, which sits on top of our compute library, which consists of code optimized to run on the wide variety of processors that you find today on your platforms. And of course, for different partners, we find different platforms. From Cortex-M, which is actually being used much, much more than we expected, for processing for keyword spotting, audio phrases, etc., through Cortex-A and Mali GPUs being used for higher performance applications, On mobile today, you've got the applications from people like Google and Facebook that are already using ML on mobile, on CPU and GPU today. And finally, of course, we're going to need to support these new dedicated neural network processors, and not just the ones produced by my group at Arm. We need to be realistic about this. This is an open field. Lots of people are going to come in and innovate in this space, and we need to allow, and more than allow, we need to encourage that. The performance and efficiency of these new neural network processors is so high that they're not only accelerating the top right, where people want absolute massive performance, but it's also making possible new applications by dint of that efficiency and that capability. My favorite is things like full frame rate, full resolution scene identification being used to drive picture quality improvements in set-top boxes. This is not a mobile application. This is guys going, oh yeah, well, we used to sort of work out what was in the picture, and then we lovingly hand polished all these pixels to make it look good. Now we're just throwing away the front end. We'll put it all through a neural network, we'll identify what's in the scene, and then we'll polish it according to our secret sauce. So with Project Trillium, we've started, we've got this ball rolling, but we need your help to do the next part. Talk a little about experts, as indeed Chris was talking about. It kind of looks as though ML is simple. You just throw everything at a neural network, and it, out the solution pops. Everyone knows what part of an image a cat is, or indeed a hot dog. Even a one-year-old child can recognize a cat. Well, it turns out there's actually some interesting wrinkles there. A one-year-old child shown a picture of a Manx cat, which is a cat genetically having no tail. The one-year-old child says that's a cat, but it's got no tail. It's confused, but it knows it's a cat. You show it to most deep learning network systems, and they go, no idea what that is. Models have hidden problems. For example, it turns out, if you're not careful, snow was being used to identify pictures of wolves. You thought it was identifying a wolf. Actually, it was fixating on the snow. You just didn't notice that until you brought a husky along, and the husky gets identified as a wolf because the husky's rolling around in the snow as well. There was another one where tanks were being identified by the bright conditions when the photograph was being taken. It wasn't actually identifying the object itself. Speech recognition works well because we've now got a combination of classical approaches, things like extracting the features via FFT, working in the frequency domain, taking out the phoneme extraction, and then working on sentence probabilities and things like that. Well, actually, if we rework that and take the phoneme and the sentence probabilities together, throw it into a machine learning model, we get a huge improvement in accuracy of speech identification. That work's been achieved because you've got researchers from one field standing on the shoulders of a huge body of research already being done in other fields. Experts are very much still needed in this space. We are a long way from making this idiot-proof. Worse than that, we've got to provide an environment in which the experts can work with each other, because we are going to need the experts to combine their expertise. So there's a lot of talk about ML being the Wild West, and in some ways it actually is. But we've got a lot to work from, albeit several places where there's unnecessary separation, duplication, and some religious wars. Clearly, no field of human endeavor in computer science would be complete without some good religious wars going on, and we've certainly got some of those. We've reached a natural position where several companies have produced systems that understand their data and produce useful results out of their data and understanding their problems. But it's now getting to the stage where we want to consolidate shared interests and try and address some of this fragmentation and duplication. We don't need so many intermediate forms. Indeed, I'd argue some of the intermediate forms aren't really intermediate forms at all. Just F-writing your internal data format out to a file does not make it a standard. There are several out there that are not thought through formats that we can use for multiple tools and frameworks and inference engines to use. We need to embrace other people's work here. We need open standards, open data representations. So we need to be able to work on that in an environment where people can collaborate in an environment like Linaro. We need to share the inference code bases. We've already got good results with ARM and Google sharing Android NN using some of our optimized code and scheduling code. We're seeing good convergence on Android with tools and frameworks. Android NN, absolutely the standard in this space. But the same's not yet true of other variants of Linux. We're seeing far more fragmentation. We're seeing those inference engines often exploiting ARM compute library for performance, but we need to consolidate on a single inference interface. There's really no need for multiple places in this space. With that in mind, we might be able to tame some of the worst of the Wild West. I talked about the three pillars of the problem earlier, the domain experts, the ML experts, and the platform experts, and how we need to bring these pillars together to make this possible. The prize at the end of this would be to allow experts in one of the areas not to have to be experts in all three. Because if we don't fix that, this simply isn't going to work. Nobody, or very, very few people, can become experts in all three of these problem spaces. I'm sure it is obvious to all of you that Linaro is the place where we should be able to work together, ARM and yourselves, to help solve the platform part of that problem and make those platforms useful and available to other developers. And this isn't, although I've talked about a lot of the usual suspects of ARM, Linaro, Google, and Facebook, this isn't just them. This is huge. The ecosystem for this is pretty much everybody you might care about. There are experts in data services who understand how to interpret and understand that data. There are experts in algorithms being used to solve the common problems, packaged up for others to use in a way where they don't have to understand them so deeply. There's companies building software services around this. There are companies and developers building tools to debug and optimize our code. And of course, there's lots of companies working on the many platforms and IP components of those platforms being designed across all the variety of end market segments. And all of these people need to be able to speak common languages and be able to talk to each other. I hope I've made clear that all this requires us to come together and collaborate as developers. We want you to join the work so that we've got the best minds working on this. ARM-NN and the compute library, as I said, were already available under the MIT license, but we got many requests to get to it closer and to be able to contribute, and that's why we're opening up the code and getting it governed, open source governance as well as open source license, in order for people to contribute. We think it's really important that we get this right. It's taken us over 100 man-years of effort already to work on ARM-NN, the compute library, all the work we've done on performance analysis, methodology, and benchmarking. And ARM has been and will continue to be committed to development on ARM-NN, but now we'll do it in the open with you and all of your contributions. We hope to leverage the best of Linaro's forte for combined development, which is key because we need your methodologies for continuous integration and testing to make progress in this fast-moving space. And we need Linaro's approach of collaborative development, making this the place where the smart people want to work. But let me be clear, of course, ARM is in no way backing off this now. This is just the start. I'll talk a little here about what's so important about ARM-NN. What did we get for those 100 man-years of effort? Well, one of the design choices from the start was not to produce our own high-level framework. There are enough of those already. Personally, I would argue way too many. Keep going. The industry won't continue to support 20 of these frameworks. They simply won't. It's also instructive to observe if you look at effort as measured by open source commits, you can see that one or two are absolutely streets ahead of the others. But ARM-NN is not taking sides in this. ARM-NN was designed from the start to plug into the existing frameworks. We're not taking sides in this war. In subsegments such as mobile, there are existing inference engines, and of course we can connect to those, work efficiently with those. There's simply no point in reinventing the wheel for Android. But for embedded Linux systems, we need to start setting some hardware standards and taming some of this Wild West. And finally, we have highly efficient backends already optimized for some of our CPUs and GPUs. We spent tens of man years of effort just on that alone, and we want the world to take advantage of that. I said we're committed to allowing other third-party IP into this. We've got 3 serious companies working with us already, looking to integrate their accelerators into our framework, and we are committing to helping that, making that possible. And it's also worth noting that ARM-NN is already proven in production. We have already more than 1 deployment shipping in high-volume production devices. Drawing to a close then, please make the most of this day. There's a full day session on this in this room following the keynotes, and I highly recommend you make full use of this, as well as grabbing people in the breaks, talking to them, including myself. In Rob's talk, he's going to give an overview of the ARM-NN design and code base. He'll talk about the interfaces, why they exist, and what they are. He'll talk about how people are using it today, and also give a peek at the future of some features that ARM are going to be contributing to the code base in future. After that, we've got Pete Warden and Mark Charlebois from Google and Qualcomm, and I'm sure those are going to be great as well. And these are just the morning sessions. We go on in the afternoon with talks from AWS, NXP, Xilinx, and others. Talk to each other. Let's work out between us, because between us is the answer to this problem, how to speed development on machine learning on more use cases across the widest variety of ARM-based platforms. Thank you very much.
Thank you very much. We won't do a